Well, in the direct formalism, it's possible to get a formal solution to the Schrodinger equation that is used primarily in higher level quantum mechanics courses when they begin perturbation theory and looking for approximate solutions. But at least we can get a formal solution to the Schrodinger equation. Remember, in the Dirac formalism, we have this as the Schrodinger equation, and it describes how the state function psi of t evolves in time. It's governed by this Hamiltonian operator, which I assume that we have. We know how to construct those anyway. And then I can I'll assume that we have some initial state, so I know psi at time t equal to 0, and I'd like to find this state psi of this ket psi of t for all time t. And the way one approaches it is you can just recognize really here, this is very similar to a first order differential equation with a little bit of a twist in that these have an operator over here instead of a constant term. And I'll just jump to the solution, really by analogy with the ordinary differential equations. I'm going to introduce this exponential, this operator that's an e to the minus I over h bar Hamiltonian operator times time. Okay? And we first have to give some interpretation of that. And the way you interpret any function of operators is in terms of its Taylor series expansion. Okay? And for this exponential, that's well known. Exponential e to the x is x to the n over n factorial sum from 0 to infinity. And the only thing we do is substitute in the, for x, we have this expression here. So that's what I'll really mean by this. In general, when you have to calculate it, you're going to have to expand all this out and then operate onto some wave function with this. Right? But it's an easy way to represent this infinite sum anyway. And now I'll just say, well, let's consider this function here, in which I take the I presume I know the state of the system at time t equals 0, and I operate on it with this operator, this exponential operator, and get a new wave function, which I'm going to call psi of t for right now. And now then I'll just show that that's a solution to the above equation. I can take the time derivative of both of these sides. This side is just the derivative of here. This one is the derivative here, but if you look at this, there's no time in the ket vector. It only depends on this operator. And one can differentiate that with respect to t. You really have to do it in this whole series, and then sum it back up. But what you find is that this derivative of this operator behaves exactly like you would expect with this parameter t in it anyway, with respect to that. And you simply get minus I over h bar times h operator times this operator back again. Now that doesn't hold for all cases, but it does for the case where this is a Hermitian operator and is like the Hamiltonian is, and it obviously commutes with itself, and so this operator h and this e to the minus I h bar t are also commute with each other. So I won't show that, but they do. And so we have this expression here, that d psi d dt on this ket psi of t is minus I over h bar h. But now I notice that this is just what I call psi of t up here. So I can plug in for this operator operating on the 0 state. I can plug back in and combine these to just get psi of t. and then multiply through by h bar, multiply through by I, and I get IH bar. So that obviously is the Schrodinger equation. So what I've just demonstrated is that I have, if you give me this equation, then this is a solution to it. In effect, you have this a continuous unitary transformation. This is a unitary. You can check that out, but it is unitary. I multiply it times its Hermitian conjugate. That's just the inverse, and then multiply to 1. And in effect, this is a unitary operator that transforms the state at time t equals 0 to the state at any time t. And as I said, it's unitary. And we've got this unitary transformation here where u is this particular operator. So we've got a formal solution. It's formal in the sense that you don't generally, it's not generally possible. It is sometimes possible, but not generally possible for real systems to use this to get the solution at any time t. But it's often used as a starting point in approximate solutions in certain perturbation theory calculations, which most quantum mechanical problems can't be solved exactly. They have to get an approximate solution, and one way to do it is go as far as you can from this formal solution.